I'll start the recording here. So this is the most application-oriented lecture. Because diffraction gratings are devices that are used to make diffraction patterns that are used all the time in spectrometers, for instance. The double slit diffraction is not used all that often. However, diffraction gratings are. So let's start by just discussing what is the difference between a diffraction grating and a normal double slit device or multi-slit diffraction aperture. You may have seen these before in other classes. Sometimes diffraction gratings are covered in modern physics. If not, what a diffraction grating is essentially a slab of some material with a periodic modulation of some sort that modulates the transmission on one of its surfaces. The simplest version is the one that's mostly used all the time, at least for what we call transmission gratings. It's an array of many open slits arranged in a line. And the main experimental difference here is that as you add more and more slits to the pattern, for instance, here in this figure, you can see our single slit diffraction pattern that we calculated last week right at the top, right here. And then the double slit pattern, we also calculate it. As you add in a third slit, you can see kind of a trend forming. The more and more apertures you add to the transmission surface, you get smaller and separate constructive fringes that are spaced further apart and are brighter. So you could definitely see this pattern board forming as you add 3, 4, 5, and then we jump to 7 slits here. We have these widely spaced, very narrow constructive fringes that are easily resolved from one another. And if you add even more slits in, this pattern becomes even more pronounced. So you get smaller, brighter constructive fringes that are spaced further apart. As a cartoon for what this pattern looks like, we could see something like this. We can imagine taking this structure with our modulation of the transmission. So that's kind of what this bumpy surface here on this block represents. And we could hit it with light, and light's going to diffract to make these separated, one center bright fringe, and then other bright fringes as we go out to the side that are much more resolved, that are separated from the center fringe by a much more definite destructive interference position or dark fringe. If we hit the grating with multiple different colors, the bright fringes for the colors all have the same center fringe position, but the outer fringes, the fringes off the center of the viewing screen, the colors diffract at different angles. Larger wavelengths will have a constructive fringe further out from the center than smaller wavelengths. So if you hit a diffraction grating with with a non-monochromatic light source, something with multiple wavelengths, or a white light source, for instance, you will get these constructive fringes off-center that have these kind of rainbow patterns, with the larger wavelengths being further out. And of course, I'm only showing 3 of the constructive fringes here. The center, this is what we call the 0th order, and then the 2 first order fringes. Sometimes the one is called the minus first order for the negative diffraction angles. But of course, there's others out here. There will be a 2nd order and a 3rd order. They'll be dimmer, of course, but we're going to compute today what those angles will be. One of the main reasons this is really useful for instance, spectrometers and spectroscopy is that it allows us, the kind of very separated nature of the constructive fringes allows us to really separate different wavelengths and direct them to different positions on a screen where we can measure them and their position correlates to their wavelength. So this allows us to these devices really do this much better than a double slit, for instance, can, and definitely much better than a single slit pattern. So diffraction gratings are used to separate colors of light, kind of like prisms, for instance, except the diffraction gratings separate the colors much more quickly over shorter distances. So they tend to be preferred these days to, for instance, prisms to separate different wavelengths of light. So we're going to talk about how we predict where these positions are today, and also how this works in an application standpoint in a spectrometer. So starting with the mathematics, it starts just where as with all other diffraction problems, we start with the Fraunhofer diffraction integral, the Fourier transform of our function describing our aperture. So here, we need a function that describes this periodic array of transmitting and non-transmitting positions, so this periodic array of open slits. I'm going to start here with a not very realistic, but easy integral to compute version here for P of x. I'm going to assume that the transmission has a sinusoidal pattern, meaning that the transmission goes up smoothly and then decreases smoothly as we go from one slit to another. Obviously, that's not true. The slits go from, it's more of like a square, multiple square functions where it goes from 100% transmission to 0 to 100, then to 0 again. And we're going to look at that integral in a second, but it helps to kind of look through this kind of crappy approximation of the problem first. So if we wanted to use this sinusoidal approximation, our transmission function might look something like this. We have some baseline transmission, perhaps that's 0, perhaps not. And then we have this other term that causes the transmission to go up and down as we move across the aperture screen. So if I draw this over here quickly, our diffraction grating might be something here where we have these multiple slits that are open, allowing light through. And what we're saying is that our transmission looks like this. It jumps up, then down, then up, then down, then up, then down, up, down, depending on when it's open. And how it jumps follows a cosine pattern. Bad approximation, but an approximation nonetheless. So we're going to take this aperture function, plug it into our Fraunhofer diffraction integral, and do the Fourier transform as best we can. And then replace kx and ky with the coordinates of the positions on the viewing screen. Same pattern as all our previous problems. So plugging this in there, let me briefly erase my quick drawing. Plugging this all into the integral, we get something like this. The y integration is again not going to matter because we're going to assume our diffraction grating is really long and tall. So this reduces to a one-dimensional problem. I know there's a typo here. I'm still calling this e of kx, ky, but it's really just e of kx. So I've color-coded the two terms here. And what we can do then is distribute our exponent to each term. That gives us a sum of two integrals. What I'm going to state here is that, so if we're integrating over the entirety of the viewing of the aperture screen here. So the integral goes from minus infinity to infinity. This integral as written, I'm going to state that you probably have seen this recently in quantum mechanics, is that this integral defines this thing. It's one of the definitions for this thing we call a delta function. In particular, the Dirac delta function. So what we're going to see is that since we have a sum of integrals here, they each define a delta function with a peak at a different point. So what we're really going to see that we get here is that our diffraction pattern is going to be this series of delta functions that each represent a really thin, narrow, bright, constructive fringe at a particular position. Again, it's an approximation, but a good one for a diffraction grating. So just to kind of show you how these things align without kind of delving too deeply into the calculation, this term, the term in blue, when we multiply by the exponential and integrate, that's the basic definition of a delta function centered at kx equal to 0. When we have this cosine term in there, we could rewrite that cosine as a sum of complex exponentials and then distribute everything, and we get two more integrals there that each define a bright delta function peak right where, when k is equal to 2 pi divided by a, here a is the period of our, or the, I guess, yes, the period of our cosine function for our aperture. And so we have two delta function peaks, two bright constructive fringes at kx is equal to 2 pi over a, and kx is equal to minus 2 pi over a. So this gives us essentially 3 bright fringes. If we use our standard conversion here to convert kx to coordinates on the viewing screen, what we see is that the position x prime on the viewing screen, or the positions where we get bright fringes, are going to be, for the blue term here, right at 0, right at the center. And then we get another bright fringe at the position z lambda over a. Z here is the distance between our aperture or diffraction grating and the viewing screen, just like it was before. Lambda is the wavelength of light. And a, the period of our cosine function, essentially tells us the spacing between the slits to a reasonable approximation. And we have a bright fringe at minus this position and at plus this position. Is this, so I know I'm not going through the definition of the delta function, but remember, the delta function can be defined as an integral of this e to the minus I kx dx from minus infinity to infinity. It's one of the definitions of the Dirac delta function, and I'm making use of that here. So without going through and showing the, I know I'm skipping the step there where I'm kind of distributing and rewriting the cosine as a sum of complex exponentials, but does everyone understand what this delta function means? And again, how I'm, again, using this conversion to get the position on the viewing screen. X prime, again, distance from the center of the viewing screen. Okay, any questions, please ask now. If not, what we're going to do is now try to take this toy model and make it more particular and more like less of an approximation. So we want to get away from this periodic sinusoidal modulation of transmission to really have like a square wave transmission where the transmission turns on and off, kind of more like what you would expect for an open slit, followed by a block, followed by another open slit, so on and so forth. And luckily, we can do this just by using some of the math of Fourier series. So just drawing here at the bottom of the slide, what we really want for our transmission function t of x is something that looks like this. So on when we have an open slit, then off when it's blocked. When we get to the next open slit, the transmission immediately jumps up to 100% or 1, so on and so forth. Now, integrating a lot of square waves, like from 0 to infinity like this, obviously that's not something we can set up to do for an infinite or many number of slits. It would take forever. But we could play some tricks with Fourier series. So remember that a wave of any shape can be written as a sum of cosine or sine waves, as long as you pick the coefficients properly. So we're going to make use, at least conceptually, of this fact. Just calling, before we move forward, each of these terms here, this is our 0th order diffraction. Let me erase some of my drawings. 0th order, minus 1st order, and 1st order. Our next better approximation is going to give us the higher order constructive fringes. One last thing before we do that higher order approximation, however, something that's useful besides just the position on the screen is also the angle that the bright fringe makes with the center of the diffraction grating. That angle can be given just from what we've already computed. So here, that angle just from small angle approximation and trigonometry will be x prime over z, the opposite and adjacent sides of this triangle. And plugging in and getting things to cancel is just wavelength of the light divided by the spacing between the slits. Lots of stuff here, but let me talk you through it. I know this seems kind of crazy, but what I want to do is make an analogy to our toy example to just kind of discuss how this problem is going to go. So if we want a square wave for our transmission function, basically what we need to do is add in more sine and cosine terms. Our square wave is just going to go from 1 to 0. And we're going to set it up so at t is equal to 0, or at the center of the diffraction grating, we're going to have the center of an open slit. So it'll be an even function. That means in order to get our square wave, we need to add an infinite series of cosine terms, each going up and take all of these even frequency components. Luckily, we don't actually have to go through and, to get the basic idea here, we don't have to go through and compute the different coefficients, because all we need to know is that each of these two new terms we add, just add 2 more delta functions to our solution for the diffraction. For each term we add, it adds in. So for instance, if we add just this second term to get a slightly better approximation of a square wave, all that gives us are the delta functions for the -2nd and +2nd order constructive interference peak. We could use the same formula to get our position of that peak on the viewing screen. And the only thing that changes is we have a constant out here that is, instead of 2 pi, we have 4 pi. So the position on the viewing screen moves out. Instead of 1z lambda over a, we now have 2z lambda over a. Similarly, if we add in a third term, we're going to get a third and -3rd order bright constructive interference peak at a higher position, -3z lambda over a. So on and so forth. If we use a perfect square function and we really did this for the infinite series, we would have many orders, but they would all follow this pattern. So really, the only thing we have to do is solve that first toy problem we did, and then kind of recognize the pattern. And of course, know conceptually what a delta function is. So luckily, we don't have to go through this problem, and I'm just kind of showing you the net result. And we're going to kind of get the pattern and then put together a simpler formula that allows us to predict where these peaks are, given the wavelength. So in order to do that, what we need is the formula for the angle of each bright fringe on the last slide, and our formula here for our position on the viewing screen. So let's go see what that looks like. When you put this out, when you kind of really try to figure out the pattern here, the pattern starts out looking like this. So basically, an integer number of the wavelength is going to be equal to the space between your slits times x prime divided by z. Making use of the small angle equation, or the small angle approximation, we can generalize to larger angles as we move out to the larger order fringes, and get that what we call the grating equation, the equation to predict where all these bright fringes are, is here. Space between the slits A times the sine of the angle of the bright peak you're looking for is equal to an integer number times the wavelength of the light. So if you're using red light, lambda would be 600 or so nanometers, 650 nanometers. So if you have red light hitting a diffraction grating and you're trying to find the angle for the second order bright peak, the second one out from the center, you would plug in m is equal to 2 here. Plug in the space between the slits in your diffraction grating and solve for the angle. It's better to use this equation in the non-small angle limit because diffraction gratings, the bright peaks can be really far out at non-trivial angles. So we're mostly going to consider light hitting the diffraction grating at normal incidence. But if your light's hitting the diffraction grating at an angle, you can do a more complicated analysis to eventually end up getting this slightly modified version of the grating equation. So usually when you work with gratings, and it's quite nice, you never have to go back to the Fraunhofer Fourier transform integral. You can just start right here at the diffraction grating. But part of the advanced optics class is to show you kind of where this comes from. If you worked with diffraction gratings in modern physics, you've probably seen this equation before. But now you know that it's kind of, this equation is built from as kind of a summary of this pattern we get from the Fourier transform of the diffraction grating aperture. So the other benefit, this result can also be derived just using geometry. I think it's the less interesting way to do it, and you learn less physics that way. The other benefit of the Fourier transform analysis is that if we didn't drop all those other terms in front of the integral, the Fourier transform could, at least in theory, tell us the intensity of all the bright fringes. Though often that's less useful, it is one thing that is theoretically possible with the Fourier transform approach. So most of your homework for this section is going to be involved looking at and using the grating equation. So that being said, that's kind of the new theory for today, and I'm going to just talk to you about some applications now that'll kind of come up as you talk about your problems or look at your problems for this section. In particular, what I want to point out is that transmission gratings can be both transmissive optics, like we're talking about here. They could be something that light passes through and then diffracts, but you could also make them from mirrors and get the same effect. And those are called reflection gratings. And you can make them by doing something like this. So for instance, here we have an input beam hitting a mirror that has this sawtooth cut to it. Each little sawtooth can be modeled as a perfect mirror that follows the specular reflection. That means the law of reflection. Incident angle is equal to reflected angle. But given the input direction of the light beam, the light's going to hit each different sawtooth mirror at a slightly different angle, bounce off in a slightly different angle, and end up giving a diffraction pattern. Each different sawtooth mirror acts like one of the slits in our diffraction grating. And we do get, the only difference with this type of grating is that it diffracts in one direction more than the other. So for instance, for a reflection grating, you might only get the positive order constructive interference peaks. You still theoretically can get inefficient negative order peaks, but they're much dimmer. It's kind of represented here by this dotted line. So kind of using a numerical approach of the what we've done here in class today, engineers are able to build these things and actually make these sawtooth reflection grating mirrors that you can buy from companies like Newport and Thor Labs. And often they're much easier to manufacture than transmission gratings, so they're honestly they're what's more common in the lab. The other benefit of using them in the lab is that they concentrate the energy into less constructive peaks. So if you need to spread out a beam or separate the different colors in a beam, but you don't want to lose power as much, a reflection grating will give you less constructive peaks because those negative peaks will be much dimmer and your energy will be more concentrated in the bright fringes that you're actually going to use in the remainder of your experiment. So that's the other benefit of this type of structure. But really the reason we use them is because they're much easier to manufacture than a transmission grating. Where you see this effect, you've almost certainly seen reflection gratings in your daily life. The back of every CD or DVD is a reflection grating. So if you've ever seen this pattern of the rainbow effect when you look and tilt a CD or DVD in a light source, you'll see something like this where the light hitting off of it gives you this rainbow pattern. That rainbow pattern, what you are seeing is the first order diffraction constructive interference fringes for the different colors in the white light that's hitting the CD. The reason it acts like a diffraction grating is because digital data is encoded in a CD by making these tiny grooves in the plastic. And everywhere there's a groove, CDs are read by shining a laser at these grooves. And if there's no groove, the laser reflects back into a detector representing a 1. If there's a groove, it's diffracted away from the detector and the detector picks up nothing, and that's representing a binary or a logical 0. So while they're not really made to be gratings, the size of these encoded divots in the CD are small enough to act like these blazed mirrors or this sawtooth mirror pattern. If you want to see this other picture is a picture from, oops, all right, going back, an optics catalog showing you what these things kind of look like. This is of course kind of a cartoon image, but it's more or less, this is what a reflection grating would look like. It's a block of glass with a silvered surface, and in this silvered surface, this sawtooth pattern is etched. When working with diffraction gratings, they can be quite expensive. As you'll, part of one of your homework problems is going to be look up a diffraction grating to order and finding the right properties. So you'll see what these things can cost. But they're very expensive and they're also very delicate. One of the most delicate optics you can use in a lab because you have to be very careful of how you handle, touch, and clean them. And they're more delicate even than the back of a CD. It's not just that you don't want to scratch them. Some of these gratings, especially if you need very small widths A, giving you much larger diffraction angles for your first order diffracted fringes. What you need is really, really small sawtooth pattern here. And those tiny changes in the height of the mirror are very delicate. Even touching that front surface, even with like a cleaning wipe or something like we used in lab, will completely flatten and destroy this pattern. So you have to be very careful not to touch the front surface of a reflection grating. Because you could take a very expensive optic and immediately make it useless. So something to keep in mind should you ever end up working with one of these things. Never touch the active surface of a grating. If you need to clean it, the best thing to do is to use a spray. If you need to get dust off the surface, use an air spray bottle at a very shallow angle. Never touch it or wipe it or do anything. So this is what they look like. This is where you might have seen these. Let's see how they could be used in the application to measure wavelengths of light in a spectrometer. So the actual problem I like to talk about and discuss here is what is a basic spectrometer? We talked about this a little bit before. And basically, the idea of a spectrometer is to take a light source composed of multiple wavelengths and focus those wavelengths to different spots in the detector. By measuring where that spot is, we can work backwards using the laws of geometrical optics and the laws of diffraction gratings, the grating equation, to figure out what wavelength must be focusing there. If you're using visible light, of course, you could just look at the pattern and see the different colors, but sometimes we might want a more numerical measure of the wavelength, in which case we need to go through the mathematics. So this is a picture of what this can look like using a transmission grating. Usually it'll be a reflection grating, but it's easier to draw this way. So we have two colors coming in. Perhaps they're light being given off by an excited hydrogen gas or something. They're both somewhere in the red range. They hit a grating, they diffract at different angles, and then a lens takes those, can take the first order diffraction fringes and focus them down onto a detector. And since they're going off at different angles, they'll focus at different points. The size of the focus spot, our beam waist, we'll say from lab, we might call that 2 W0 here. And really, what we want to know is, what are the closest two wavelengths a spectrometer can actually separate this way? Is there some limit to it? Like maybe we can tell 650 and 700 nanometer red light apart. But will the same diffraction grating be actually able to tell apart 630 nanometers and 629.8 nanometers? Sometimes you might want a really accurate estimate of what your absorption line is in a gas, for instance, if you're a chemist. So what limits this? What are the limitations? What are the what properties of the grating or this lens system determine that? So that's the kind of example I want to work through today. And it'll give you one more formula that you're going to end up using on your homework. So here, for instance, here is some like geometry here. The other thing, D is the total size of the beam of light hitting our grating. And after diffraction, depending on the order we're talking about, the size of the beam after it comes out of the grating will be D times cosine of the diffraction angle for that constructive fringe, whichever one we're using. Usually it's theta 1, the first order fringe. The others, the further out orders, tend to get too dim. So we can kind of use this to get an initial measure of our beam waist, quote unquote, or a radius of our beam before the lens. And then we can kind of, so that we could call W0. W prime will be the radius of the beam spot after we focus it down on the detector. And the key point here is that two wavelengths, if they're nearby to each other, two very close wavelengths, we'll be able to tell them apart as long as we could focus their beam spots completely to different spots. They don't overlap at all. So we would need the two wavelengths to focus to points that are separated by at least one beam spot diameter. By at least one diameter, 2 omega, or 2 W0 prime. So it's very similar actually to the Rayleigh criterion we talked about at the end of our last class. So if we wanted to figure out what this was, using just the geometry here, we could figure out what this beam spot width will be. So here, F is the focal length of the lens in our spectrometer, not the frequency. Keep that in mind. But we can see that here, this is taking some results from our going back to the lab on beam wastes and Gaussian beams. So it's been a while, I know, but this comes from that lab, how the beam waste changes after a focus. So if you don't remember that, take it on faith for now, but you could go back to the lab material to see this is that formula. And then we could just kind of plug in the results from the geometry here. using our formula from that lab to get the size of this, or the radius of these beam spots in terms of the wavelength and our diffraction angle and the focal length of our lens. So we can predict how big these spots are. That's the takeaway message. And we need the spots for our two wavelengths to be separated by at least 2 times this distance. The other thing that is useful then is sometimes it's useful to determine how far they're separated in angle as well as distance on the screen, because we might put the screen at a different angle. So we could call that difference in diffraction angle delta theta, as on the slide. And so if we want to relate delta theta to this, the separation distance on the screen, we can multiply by the distance they travel. Ideally, if we have things focusing correctly, that distance will be focal length. So F delta theta will give us the actual separation. So what we need to do if we want to determine whether these beam spots are separated by the right distance or enough distance, we compute what that distance needs to be, W naught prime, and then we compute how far they'll be apart on the screen by multiplying the focal length by delta theta. If focal length times delta theta is bigger than 2 times W naught prime, then we'll be able to tell the wavelengths apart. The only thing that's left is to figure out what this delta theta will be for 2 different wavelengths. So we can get that just by doing some like calculus, we can say, on the grading equation. So let me go up and put our grading equation as we started it on the slide. I'm just going to type it in here in a second so you guys have it. 1 second. So our grading equation, remember, was our slit spacing A times sine of our diffraction angle is equal to m times wavelength. M being the diffraction order we're talking about. So if we want to get a small measure of what delta theta might be, we could do some sketchy first semester calculus. So we could take the derivative d theta d lambda and use this, use the grading equation. So we could do d sine theta d lambda on one side, take the derivative of the other side with respect to lambda. The chain rule will give us a d theta d lambda in there, and the derivative of the sine with respect to theta will give us a cosine, and we could rearrange and get a formula for d theta d lambda. And then doing what math professors have always told us we can never ever do, split the derivative into 2 differentials and get that our change in diffraction angle for the different wavelengths is proportional to the difference between the wavelengths. So delta theta is proportional to delta lambda. And this is also proportional to the grading, the order, the constructive fringe we're measuring. So m for most experiments is usually 1. We usually use the first order angle. And then what we are going to do, cosine of theta of m, that's just computed for the first order angle for one of the wavelengths. Usually you could pick one or the other. It's a good enough measure either way. So we compute that using the grading equation. Give me 1 second. Zoom is kind of being a pain and is not letting me move forward on the slide. There we go. Okay. So we have a measure for delta theta, and we know that F times delta theta needs to be bigger than 2 times the width of the beam spots, W naught prime. So let's compute. So focal length times delta theta will give us this formula. And we're going to simplify this in the end, so these are not the formulas you'll end up working with here. I'm just kind of showing you the derivation. So kind of simplifying, rewriting, multiplying and dividing by 2, just to get the formula for W naught in there. So if we want the minimum distance here, the minimum separation possible, we need this term to be equal to 2 times the beam width after focus. So we could plug in the formula we have for that and work through simplifying things a lot. Getting things to cancel, combining cosine theta terms, so on and so forth. We'll see that the cosine theta ends up canceling out, as does the focal length of the lens, so it doesn't matter. Our end result here for the smallest wavelength distance we're going to be able to measure, delta theta, does not depend at all on which order of the diffraction grating you pick up on your detector. It does not depend at all on which lens you use to focus the light. It's a general result, which is pretty nice. So the solving for delta lambda, the smallest wavelength difference we can detect will depend on whatever center wavelength we can say, or average wavelength we're using. So lambda might be the average wavelength of these two colors if they're really close. Our slit spacing, and the size of the beam going into the diffraction grating. M is the order of the diffraction peak we're using again, and that's equal to 1. So we can rewrite this here kind of like so. So N will be the number of what we call grating lines, the number of open slits that are actually being hit by light. So we can see M times little, the ratio D over A will give us the number of slits that are actually being hit by light and working in the problem. So the smallest wavelength difference that we can detect with any given diffraction grating lens combination in a spectrometer is proportional to the center wavelength or the average wavelength we're working with, lambda, and inversely proportional to how many slits of the diffraction grating we're actually using. So just kind of plugging in some numbers to see what this is. Let's say we're trying these 2 wavelengths we're using are in the orange range. So lambda is approximately 600 nanometers for both of them. We're using the first order for the diffraction order that we're sending into the lens, so m is equal to 1. And diffraction gratings might have 2,000, 3,000 open slits per millimeter on the screen. This is often written in grating language. It's called lines per millimeter. So if we have 2,400 lines per millimeter and the beam going into the grating is 50 millimeters in diameter, then the number of lines that are actually diffracting light, or the number of slits that are actually diffracting light, is about 120,000. This would give us a delta lambda of about 7 thousandths of a nanometer. So we could, with most diffraction gratings, we could get really, really fine resolution. And if you want a simple order of magnitude estimate, which is really all that's useful, you can really drop the 4 and the pi from this problem. And just kind of 4 divided by pi is approximately 1. If, like me, you're lazy and you don't really want to do real math, 4 divided by 3.14, yeah, that's 1. So what we can do is get a simple formula for what we call the resolving power of a spectrometer. The ratio of the smallest wavelength difference it can measure to the average wavelength of all the light going in. And we see that really the only thing it depends on is the order of the diffraction grating you use, usually first order, and the number of slits that are actually illuminated with light. It's quite a simple estimate that is used just to get a working device in the lab. This kind of going through this problem, there's a lot in this derivation and a lot of new terms, but one of your homework problems will have you explore this a bit more and get better idea of what all these terms mean. That's the new theory for today. Let me just finish by giving you a little preview of what the problems are going to be. Yep. So you can ignore my annotation there from before, but the first problem here is just a few working with some numbers. I'm giving you different gratings with different numbers of slits per centimeter or millimeter or so on. So you have to figure out what your slit spacing is from that information, and then figure out how far apart the diffraction order is for different wavelengths that hit the grating. So what is X prime for 589.5923 nanometers versus the second wavelength, given that you're looking at the first order diffraction fringe. And we put a screen 1 meter away from the grating. You can assume no lens in this problem. Same thing for part B is, again, just numbers working with the grating equation. The second problem here looks really long, but a lot of it is, I want you to kind of get an experience I was going to give you in lab, where you're going to look at some gratings that you can find from a company like Thor Labs, see what they cost, what you can buy, and find part numbers, but then also use the information to determine whether we have enough resolution to tell apart the different frequencies that we want to measure in a spectrometer we're going to build. So this second problem will kind of have you work through using the formulas from kind of the end of this lecture. So that being said, these two problems will be due next Friday of next week, May 1st, the last, what would have been reading day. And that will be our last homework assignment for the semester. And that's the last of our material for today. Wednesday, we start lasers. Thanks for listening, and see you Wednesday. And of course, if you have any questions or anything about the lecture, I'll hang out for a bit. Feel free to ask.